Today, we are going to present TIC, a new software-defined radio that provides low latency and programmability at both PHY and MAC layer. Given the latest wireless technology, we have found new drives on SDR. New wireless standards such as 5G and new applications like drones and VR, they all require extremely low latency. And with the rapid evolutions of wireless protocols such as 802.11, PHY and MAC changes quickly. We have to modify wireless processing code to adjust to the new standard. So good programmability is also needed for SDR. However, this is not an easy task. It's hard to achieve both requirements in the existing SDR systems. For GNU Radio and Sora, they both offer good programmability. However, the latency of GNU Radio is even far below the 802.11ag requirements, and Sora has better performance, but due to the limitation of CPU processing speed, Sora still cannot fully guarantee the strict timing in 802.11ac. Warp provides a reference design that can implement real-time 802.11n. But based on its current architecture design, Warp is hard to program and implement real-time 802.11ac. Why is it so hard to ensure both low latency and programmability? From our observation, the domain-specific reason is PHY and MAC differs in their data and control flow. For PHY layer, the computation workload is very heavy, such as FFT, channel estimation. So most of the current designs are focusing on the performance optimization. People want to use hardware components to ensure low latency, which makes it hard to program. For MAC layer, it has complex conditioning and branching operations like retransmission detection and backoff. To implement these functions, people prefer to use processor and write C codes to implement. However, this makes it hard to satisfy the MAC timer. Therefore, it's hard to achieve both for both PHY and MAC. As we discussed, SDR requirements consist of two dimensions. An ideal design for SDR should achieve low latency while maintaining good programmability. For existing design optimization, PHY layer usually focus more on the low latency and MAC focus more on programmability. None lives in the ideal area. Actually, it's not a simple trade-off. To reach the best of both worlds, we need to design a new SDR. To achieve our goal, we design and implement TIC. TIC uses hardware and software co-design techniques to ensure both low latency and retain programmability. First, to address the PHY latency, we apply new parallel pipeline techniques in FPGA. Second, to address the MAC latency caused by complex control tasks, we separate data and control flows. And last, to retain programmability, we adopt a modular programming concept in both PHY and MAC. In next few slides, I will guide you through our design details. First, we reduce the PHY latency with MCDP design. Wireless PHY is pipeline-based architecture and consisting of several processing modules. Current SDR system usually uses the same clock frequency to drive the whole pipeline. We noticed that if we use single clock frequency, the maximum frequency for the whole pipeline would be limited by a bottleneck module, which means other modules can only work in lower clock frequency. We found that the problem is the different computing workload in different modules. Workload-heavy module always becomes the bottleneck. In this example, synchronization module has more complex processing, so it's the bottleneck module, and it can only run in the clock frequency of 45 MHz. However, a much simpler interleaver module itself can work at 430 MHz. If the interleaver runs in this clock frequency, the latency can reduce a lot. So single clock limits latency reduction in non-bottleneck modules. So if each module can operate in their highest clock frequency, the latency of the whole pipeline can be reduced. Our solution is to use multi-clock domain pipeline. We apply different clocks to each module. However, it's not enough to just add multiple clocks. How does data transfer through different domains? We thus use asynchronous FIFO for the asynchronous communications. The FIFO also serves as a buffer. We use full and empty signal to avoid overflow and underflow. Besides MCDP, we also apply another field-based processing techniques in Phi to further reduce the latency. First, we noticed that bits are not equal in a frame. Usually, a wireless frame contains training and data fields. When we process one frame in Phi layer, the whole frame passes through the entire pipeline, which leads to the latency of the whole pipeline. Interestingly, we noticed that not all fields need to traverse the entire pipeline. For example, in 802.11 protocol, training field starts processing from FFT. If we use frame-based pipeline, when a frame passes through the modules before IFT, training field doesn't make any changes. So we can separate these two fields and let them start processing from different pipeline stages. In this example, training field bypass all the modules before FFT, and the latency can be reduced from 2.49 to 1.86 microsecond. So our solution is to parallel processing fields in different pipeline stages. In a real example in 802.11ac, 8 fields can parallel processing from the 3 pipeline stages. Field-based processing is a flexible design. We can customize the pipeline stages for fields with necessary information, for example, fields quantity and its order. For example, 11A and 11AC share the same fields with the legacy header. If we want to update 11A pipeline to 11AC pipeline, we just need to add new control information for the new fields. Now let's move on to the reducing MAC latency. We usually use embedded processor to handle MAC control logic. However, MAC also need to process data like CRC computation, which will take a long time. We thus adopt well-known Accelerator-Rich design to offload some computation-intensive tasks to Accelerator. Offload tasks do help to reduce latency, but it is not sufficient. For example, when data and control share the same path when they are working, if one accelerator wants to transfer data to another, the DMA will cost about 400 microseconds. And during this time, all the other control blocks. So we need to explore the idea of decoupling control and data flows. In this way, the embedded processor does not need to handle data flow directly and the timing-sensitive control flow will not be blocked. With this kind of design, MAC latency can be reduced significantly. So how does the embedded processor and accelerator communicate? The easiest way is to use a bus to connect them. However, it's not the best solution. First, the read and write latency is larger, and second, bus incurs repetitive control. When processor wants to send information to several accelerator, it needs to write multiple times. So we use register-based interface. The embedded processor puts control information into a shared register block to avoid repetitive write. With this design, the accumulated read and write latency is smaller. Although the reduction is small, it's worth the effort because the shift time is 16 microseconds, where every microsecond matters. To avoid the write conflict to the same register, we separate the register block into control and status register. Control register handles downlink only, and status register handles uplink only. Achieving low latency alone is not enough. Another problem is how to retain programmability in the same time. We use element-based design, similar to the click router. From our observation, modules in Phi and Accelerator in Mac has similar structure, so we can unify their interface and abstract them to an element, like this. Under this element abstraction, programs only need to focus on the processing engine part without worrying about interface design. We can further put them into an element library. The left task is to make connections in both their control and data flows, like this. We use XML-based configuration to generate element and connect them, which can reduce some duplicated programming tasks. Next, Zhengwen will talk about more on implementation.
Okay, thanks, Haiyang, for the detailed design. So let me guide you through the implementation. We have implemented 3 802.11 protocols on the TIC to demonstrate the performance merit and also the programmability. So there are 802.11ac with both the SISO and MIMO, and also there's a 802.11ag with the full duplex. They all achieve the real-time system requirements by the standards, and especially the 802.11ac implementations are the first ever real-time implementation on the SDR. So we plan to publicly release our code very soon, and this figure shows how the 802.11ac SISO looks like, and other systems looks alike. The TIC system is built upon the commercial off-the-shelf hardware. The FPGA board is an Xilinx Kintex 7 KC705 board, which is a mid-range FPGA. And the ARF board and the USB boards are also commercial products. But to the end users, the TIC is provided as a rich library which supports various wireless protocols. Right now, we support 802.11a, G, AC, and more to be added. So users can use our easy-to-use APIs to program the Mac and the Phi pipeline with our XML or the GUI we provided. They have a wide range of choices. For Phi, you have different modulations, coding rates, and modes. And the Mac, you have lots of accelerators. In TIC implementation, we do face a lot of issues, and we address them. For example, at the Phi, we need to eliminate the jitter caused by the asynchronous FIFO we adopt in the MCDP. At the Mac, we need to ensure that the critical timing accelerators are done via this timestamp passing. And even more, at the hardware and software co-design front, we need to choose the low latency interfaces to further push the system latency to the limit. We learned these precious lessons, and there are more in the papers. So next, we evaluate TIC. Our evaluation is focusing on the 802.11ac SISO implementation. The other two are left as the case study. First, we will look at the latency benchmark details compared to a reference design to show that both Phi and Mac have great latency reductions. Second, we look at the overall system evaluations regarding the latency, programmability, and also the FPGA resource usages. So first, the latency benchmark. So this benchmark is done compared to a reference design, which is essentially an 802.11ac implementation, but without the TIC design. We adopt some of the popular designs seen in the current SDR and show that TIC can further reduce the latency. At the Phi, we reduced 2.2 times in the transmission side and 1.6 on the RX. Specifically, both MCDP and field-based processing are proven very effective in reducing the latency. The MCDP can reduce the latency by 15%, and the field-based processing further push the latency to the limit. For Mac, the reduction is more impressive. Actually, we achieved more than 2 orders of magnitude reduction in both cases. Of course, the key is we adopt this Accelerator-Rich design, which offloads the data-intensive tasks such as CRC and the frame header processing to the accelerators. There are more details in our papers. So overall, the TIC achieves overall latency of 334 microseconds on this end-to-end loopback test. Notice that under the same testing condition, the warp will have millisecond level latency. And the SIFS timing is also ensured. The programmability of TIC is shown via this line of code counting. We reduced 22% of line of codes, and also because we provide user with XML-based configurations, it's easy to program. And finally, the FPGA usage is moderate, even on this mid-end FPGA, with less than 30% lookup table for the SISO case, and even for the MIMO, it's less than 2/3. Okay, so the first case study I will show you here is a real demo of our 802.11ac. I think this video somehow is not playing. So this system is the first real-time system provided in the research community. We test the performance using the 64-core modulation, and according to the standards, it requires 560 megabit per second throughput at the PHY. So with TIC, we can achieve up to 1 gigabit per second throughput for the PHY TX and 632 megabit per second for the RX. Of course, the shift timing is still ensured, and the coding effort is lightweight. For the full duplex, the coding effort is even less. We counted the line of codes we changed for, with the original AG implementation, and only 8% of codes are changed. And as you can see in this demo, we achieved the real-time video transmission, and the throughput is up to 245 megabit per second. So to conclude this work, we start from the observation that the future SDR calls for lower latency while you have to retain the good programmability. But we examine the existing designs and find that they are hard to achieve both goals. Thus comes the design of the TIC, which is a 3-year development effort at 2 universities. We explore the hardware and software co-design techniques from the computer architectural fields. And we have implemented the first real-time 802.11ac systems on the TIC. So we hope that this work can stimulate more community efforts in the domain-specific design for the new wireless networking. Thanks you for your time, and please visit our webpage. There are some more details, and we'll release our codes on the webpage. I'll be happy to take any questions. Thank you.